Yeah, hello everybody. Welcome to our webinar, Production of Reference Materials. My name is Rainer Schramm. This webinar was prepared by Susan Aschenbrenner, but unfortunately she's not able to help this today, so that's why I will give this presentation. Fluxana is an accredited producer of reference materials, and today we would like to give you an inside view of how we produce reference materials. The materials we produce are dedicated for X-ray fluorescence. So this is always our focus, that we really want to concentrate on this application method. And so in this sheet, I would like to present again how X-ray is working. So on one side, you have your sample material, which should be an inorganic material where you would like to do elemental analysis with. You have to prepare this in any way. Either you want to measure the powder, or you make a press pellet out of your powder, or you fuse it into glass as a fuse bead. And then you present this to an X-ray fluorescence spectrometer, which then is identifying and quantifying each element. And that means this results into an intensity, and via calibration, this is then converted into a concentration. So that in the end, you get a report which gives you the elements, sometimes also expressed as a component, and you get the concentration values. The idea, of course, in such an analysis is to get the highest precision and accuracy as possible. Unfortunately, an X-ray fluorescence spectrometer cannot directly quantify how much of an element is in a sample. So it can only compare. And that's why we need reference materials. That means an X-ray spectrometer, you always have to calibrate with known materials, and then you can analyze unknown materials. And in this way, then is the spectrometer able to measure and to determine concentrations. So this is the reason why we need to talk about reference materials and how we get them. There was a webinar last year where we presented already what are reference materials and standard samples. I just would like to repeat this. Especially the definition of a certified reference material is very important. Here you see the definition. It's a sample which is sufficiently homogeneous and stable for one or more parameters. So the parameters we would like to calibrate. Also, it should be analyzed by a traceable analytical method. And then this will result into concentration values with corresponding uncertainties. And very important that you can call it certified reference material is that you have an established traceability, so that we are sure the results are accurate. More and more reference material producers are accredited according to the ISO norm 17034. This is for the producers of reference materials. And if someone like Fluxana has this accreditation, this means that there is an external audit on a regular basis from an authority to check whether all the procedures comply with the norm. Also, if you have a reference material, you can say there is an X concentration, which comes with an uncertainty. And this uncertainty splits into three terms of uncertainty. So one is the characterization, that means the analysis error. The other is the between bottle, that is the homogeneity. And the third one is the long-term stability. So these three uncertainties add on to the total uncertainty, which then you will find in a certificate together with the certified concentration. Now, how do we produce or how do we make a certified reference material? And this picture here shows you a little bit the way we have to go. Of course, first we have to select and find a material which is fit of purpose. That means that it is really what we want. Then, of course, when we get it, we have to inspect it. If the material is suitable, we have to package it into bottles. We have to check the homogeneity. We have then to characterize all the parameters in that material. And then it's mostly going to the stock. And when it's in stock, we have to monitor, is it stable? And we have to monitor also if there are any issues during transport and during the lifetime and use of the material. So let's start now. How do we select a material? And there it is very important that we have a good communication with our customers, with you. That means many of you already have asked us if we are able to make a reference material for them. And this is very often a starting point. And we are then coming into the discussion if there is a material available, if there is really enough interest from other people for this material, and how much work will be involved to establish this material as a certified reference material. So it's always worth from your side to ask us and to make some proposals, because this makes sure that reference materials we have then in our portfolio are really what you need for your daily work. After we came to the agreement with you that this is a material which is of a certain interest, and then we will ask you that you make this material for us, or you take it from your production stream, and then you send us a certain amount, let us assume about 10 kilogram, and this is then coming into our stock. And the first thing what we do then is that we take the container where this material, where the complete material is in, and we take then samples, mostly one in the bottom, one on the top, and we will then analyze this to find out, is it the material we expect, and what is the typical composition, and is there already an inhomogeneity between different positions in that material. Of course, we will send this to our laboratory, and this is also working under accreditation, and in this case the 70025. That means this laboratory is accredited for XRF and can do any kind of applications which are of interest in the XRF field. And this is important when you produce reference materials, that the final purpose where this material should be used is already the case when you analyze it. And in this way, we can make sure that we see already all the troubles and all the specialities which are depending on that material, and that we can really find out what problems could appear. And is this material really fit for the purpose? So important is then that the material is homogeneous, and that the concentration ranges where are the expected values are corresponding. Next thing is that we will package this. And this is important. In the moment we think a material is good enough to make a certified reference material out of it, in that moment we want to conserve this. That means we fill it then immediately on bottles, into bottles, and seal them, and then the material is already ready in the stock and ready for use, so that all the tests we do then to test the homogeneity and to characterize then the parameters are done on the bottle, like it is sent out finally to the user, to the customer. And for the packaging, of course, we have to make sure that the material is homogeneous, that the particle size is small enough, and that in every bottle in the end is the same material and the bottle will be sealed. In the next step, when all these bottles are sitting in the stock, then we will randomly take out test materials, and this could be a number of 10 bottles. And then these 10 bottles are going into the laboratory and are sampled, also at two positions, at the bottom, at the top part. And so in this way, we find out if inside the bottle is an inhomogeneity. And of course, we sample 10 bottles if between the bottles is any inhomogeneity. Yeah, this is important to make sure that the material shows an homogeneity, which is of course not giving too much error to the total error. Yeah? Otherwise, the error in the end of the material will be so high that it's not small enough to do a calibration, because you always have to think about when you use a certified reference material to calibrate a method, the material comes already with an error, and the error in your calibration cannot be smaller than all the errors summed up from the reference materials you want to use to calibrate. So this is why it's so important that the error of the reference materials is small enough that you do not add too much error from the material itself to your calibration. So when we remember our total contribution of the three parts of uncertainties, then we have talked about now the between bottle uncertainty. And so this is how we calculate the first U from this homogeneity test. The next very important, or also one of the most important steps, is to characterize now the material. That means to find out which elements are of interest and how much of this element is in that material. And to make this, we use a special procedure here. There are, of course, different ways you can do it, but we in Fluxana have established one procedure, which is described in this chapter in the ISO norm. And this is the way that we compare our material with another certified reference material, which comes from a qualified reference material producer. This could be, for example, NIST. That means we look, is there already a material from NIST which is comparable to our material we want to certify? And then we could use this to establish an own certified reference material. Of course, mostly this fits for a few elements, but not for all elements. And so we need to have a second possibility. And beside CRMs, which are already in the market, we can also use pure chemicals to just construct or to simulate the material we would like to characterize. And so in this way, we have then the two possibilities to compare our material with. But how does it work in the real world? That we use a sample preparation fusion. Why fusion? Because in the fusion method, we can dissolve the powdered inorganic material completely. The original material is destroyed. There are no particle size effects anymore. And that means the material is completely dissolved into the glass. We have then a very homogeneous sample, and we have a very reproducible sample preparation. So the error contribution of the sample preparation has to be absolutely minimum. Yeah? And to make this, or to guarantee that this is possible, we use our own fusion system from the Vitriox electrical series. And these machines are specially constructed in a way that they have a certain automation. The temperature is absolutely stable. Then we try, of course, to use always exactly the same platinum ware, that we do not introduce an additional error. And we try to make all the tests within one day, so that there is no time dependent variation in the sample preparation. And if we keep all this constant, on these machines, we can achieve reproducibility, which is about 10 times better than you would know it normally from fusion. And this means that the contribution of the sample preparation error is so small that we can really concentrate on our characterization and can use this finally as a reference material. Then we have to compare this with the reference, with a second reference material. And how do we do this? That means from our candidate material, we make a fuse bead. And from our certified reference material, for example, from this we want to compare with, we also make a bead. And this is done on the fusion machine always alternately. Yeah? So you see one from this, the next one from the other. And so we try then to get 10 beads in the end to, so that any variation in the sample preparation is immediately taken by the two neighbor preparations. And when you do that, that means you make 10 preparation of the candidate material and 10 preparation of the CRM. Then we go to the X-ray instrument and measure them. And how does this work? If I go back, so this is prepared and then measured 2 times on the X-ray. This is prepared, measured 2 times on the X-ray. This is prepared 2 times, and so on. So that in total we have 20 beads we want to compare in the end, measured 40 times. And this gives then the results. That means the first bead is then measured 2 times. This is our candidate. The second one, prepared from the CRM, is measured 2 times, and so on. And here I have an example that we measure aluminum oxide in an iron ore, and this is prepared as fuse bead. And what you see now is that when we determine the aluminum oxide in the candidate material, we are around 1.5%. And in the CRM we want to compare with, it's about 1.1%. And we calculate then the mean value of these 2 measurements, and then we get a difference. This difference tells us the deviation between the iron ore we get as a certified reference material from an external source and the iron ore we would like to certify. And now you continue doing this, and you see then that you get in the end a mean difference between the 2 materials. Of course, then you can calculate a standard deviation for this calculation, and this will then result into a standard uncertainty of this mean difference. Yeah, so we get from this procedure already an error in the characterization, and you see how low this error finally is on such a kind of preparation and characterization. So remembering, we have this difference and we have this uncertainty from these characterizations. Now we read in the certificate of this CRM how much aluminum oxide is really in that iron ore. Of course, this also comes with an uncertainty. And now we add here our difference. And so we know now that in our candidate reference material, we have 1.403 aluminum oxide. And the uncertainty we have is then calculated together from the uncertainty from the certificate of the certified reference material and the uncertainty on our characterization. And now you see that our sample preparation is way better and the contribution of the error is lower than what we get, of course, from the certified reference material. And this is what we intend. We don't want to introduce an additional error. So this means now we have our second component, the uncertainty, which comes from the characterization. Of course, when you just do in one laboratory, one characterization, there's always a risk that you are off the real world, that you have an error in your method or whatever. Yeah. So this is why we mostly organize a round-robin study with the same material before we start our characterization. And that means we have then, like in this example, 20 laboratories who analyze this material already. And also from this study, we get a mean value. and we get an uncertainty. And now we have the good possibility to compare what we have determined in our own procedure in the laboratory with what 20 international laboratories have determined, who all know what to do. Yeah? And so in this way, we are always on the safe side that what we do here is really absolutely traceable. But why do we do that and do not take the round-robin study? The difference between the two sets of values is that this method we have 100% under control because it's in our laboratory, which works under accreditation. All the procedures we do on the certified reference material production is under accreditation. So every single step is under control. The values we get from the laboratories from a round-robin study, of course, we believe that everybody here is doing a good job, but we don't know. So in this way, it's not traceable. So we are not 100% sure that everybody here uses a method which is traceable to, let me say, certified reference materials. And that's why we do not link these two sets to each other. We just use it to find out if there is any systematical problem and if we have the system under control. Okay. That means when the characterization is done, we have, before we sell now such a material, we have to think about, yeah, how stable is this material now? And this is sometimes the most difficult part, because how do you know how stable your material is? And then, of course, it is very important that you have already experience with such a material. So you know from history that when you store that iron ore, this is always stable, you can reuse it, nothing can happen to it. But sometimes you have materials where you don't know. It is new, it is perhaps a new industrial material, and you have not so much experience. Then we really have to do a lot of tests in a very short term to find out if the material is drifting away. And mostly such a production of a reference material takes about a year. And in this year, then you have to do this intense study. And from this study already you will know what happens in a year. And then you do your estimations for the next 9 years based on this. This is the only possibility you have to get an idea. And then you have to do your calculations and find out how big is that U and how much does it contribute to the total uncertainty you will find in the final certificate. Then, finally, when this is all done, it comes to sell this material and then make it public. And what happens then? So first of all, there has to be a certificate established. And in the certificate, of course, you must find the characterized values, the corresponding uncertainty, and how traceable is that material. Yeah? And then, like in this case, you find that it's traceable to some NIST materials, or for example, to a BAM material, and so on. Yeah, and of course, all the conditions under this, how this material has to be used, so that the characterized values are in correspondence. And of course, we have to package it. We have to make sure that there is no problem in shipping, that the material is not destroyed, and we try always to seal the materials in a way that there can be no moisture coming into it, and so that over years it will be clean and dry, and nothing can happen. But nevertheless, we have to monitor the stability, and this we will do over the whole lifetime of that material. The oldest materials we have in stock are already something around 12 to 15 years. So that means we have quite good experience with these. And then you can see if the values are still in the expecting range. And when, of course, it will go out, we have to stop selling the material and to inform the users that now there is a problem and you can't use this material anymore. So if I want to summarize, to make a certified reference material, homogeneity is very important. Characterization is important. It must be traceable. the stability is important, that you can use that material as long as possible. And of course, how sure are we that the value is in a certain range, concentration range? So what is the uncertainty? And the uncertainty is always coming with a probability that let me say that we give a probability of 95%, and for this the uncertainty is valid. And last but not least, traceability is a must if you call it a certified reference material. Only then it must be traceable. And here the whole process, what I have shown you, so it starts with selecting a material. Of course, there it can be already a long story that you send forth and back material to find out, is it really suitable? And then we have to make sure on our side that the material is really fit for purpose. So, thank you very much for listening to my presentation. Here I have an advertisement for our next webinar already. And now this webinar is open for questions. And of course, you will get this presentation, and also you will find it in a few days in YouTube, again as a video. And you can always feel free to send us more questions or any proposals for new reference materials. And now I will have a look into the questions we have in the system here. How do you eliminate instrument uncertainty over long term when evaluating CRM stability over long term? This is a very good question. What we try to do is we have some reference material in our laboratory, which we know very well, and we always run them together with the candidate material we want to test. So in this way, we make sure that if the XRF instrument has drifted away, we can factorize and can eliminate this long-term uncertainty. But it is a risk, and we always have to watch it 3 times to be sure that this long-term uncertainty doesn't play a role in our test. There's another question. Don't you follow the principle of theory of sampling when you take samples? From your explanation, it seems you are actually just point sampling. Yeah, that is right. What we do is that we try to get the complete inhomogeneity, which is in that material. However, we assume from the beginning that the material is homogeneous, because when we find real inhomogeneity, then this material can't be used anyway. So that means we discuss already with the producer upfront, how is it guaranteed that this material has already a certain particle size, has a certain process of homogenization, and only then we take it, and then we just monitor what homogeneity is really, or inhomogeneity is really the case. So what happens if a CRM is not as stable as expected over long term? Yeah, it means that we in the beginning have to define when is a material stable and when not. That means already in our planning of the reference material, we define when is it out of specs and how and when we still consider it as stable. And this is what I have shown you here in that in that curve. That means when this point is then going out, then of course we have to consider it as not stable anymore, and we have to inform our users, and we have first of all to stop selling this material. Then we have to go back. Perhaps we can reissue a new certificate, but of course only if we can then again establish stability for the future. So that means we have to go back in our process and have to reevaluate the stability to take a decision if we can still sell this material in future with a new certificate, or we have to take it out of the market forever. So there is no more question. Perhaps I'll wait a few seconds if there's another one coming in. This is not the case. So then I'm very happy that you all contributed in this webinar. And like I told you, feel free to ask more questions in the next days. We are always here. And I thank you very much for listening. And I hope that you will join us the next time. Thank you very much. Bye-bye.